Afternoon. Today we will be presenting the challenge, which was the design and construction and modeling of the Mangano catapult. Our team members include Renata Reyes, Camila Flores, Carlos Valenzuela, Ana Rebeca Aguilera, and Isabela Souza. The goal for this challenge was for us to be able to estimate the trajectory of a projectile launched by a catapult. We showed the projectile trajectory of the shot in relation to the position in the x-axis versus the position in the y-axis, and also as a function of time with more specific time intervals. We decided to do a Mangano type of catapult, but our design did end up deviating a bit and turning out a bit different from the traditional Mangano catapult, since it lacked a torsion mechanism. This means that our catapult didn't have a restraining rope to hold the arm back before the release, but instead we did it manually with the help of a team member. So how does the catapult work? We will be showing that in the next few slides through the theoretical framework, the parabolic movement, Newton's laws, air resistance strength, summing forces in 2 dimensions, application of the 2D equations of motion for the catapult, and Euler's method. The Mangano is a type of catapult that uses tension and torsion to launch projectiles. A long rope is attached to the throwing arm and is stretched and wound, which stores tension. When released, the rope snaps back, propelling the arm forward. The angle of the arm affects the distance and height of the projectile. Torsional force from the rope helps pull the arm backward, creating the necessary force for launching.
Our project consisted on carrying out a projectile throw, which is a parabolic movement. When an object is in parabolic motion, it is released at a specific angle called the angle of throw. It has initial values like the initial velocity, launch angle, and initial position in the x-y components that depend on where the object was initially launched. In addition, the projectile is also affected by outside factors such as air resistance. The velocity's horizontal component is only affected by air resistance, whereas the vertical velocity is affected by air resistance and acceleration due to gravity.
Newton's first law of motion states that an object at rest will stay at rest, and an object in motion will stay in motion unless acted upon by external forces. In the case of the catapult, the object would remain at rest, in this case the ball, unless an external force, meaning one of the team members, would pull the catapult's arm to exert the force on the ball. In the case of the projectile throw, the vertical velocity is affected by both gravity and air resistance, which is why the ball doesn't continue to go up and up, but is slowed down by the gravity and by the air resistance. In the horizontal component, the velocity is only affected by the air resistance, which limits the total horizontal displacement. If no air resistance was considered, the velocity in this component would just be constant. Newton's second law of motion states that force is equal to mass times acceleration. In parabolic trajectory, air resistance is the only horizontal force acting on the object, while gravity and air resistance impact its vertical acceleration. The object's mass influences the gravitational force acting on it. In a catapult, the acceleration of the launched object is related to its mass and the applied force, with more force resulting in a greater acceleration. Newton's third law of motion states that for every action, there is an equal but opposite reaction. Air resistance opposes an object's motion, reducing its velocity and causing it to slow down. When the catapult's arm is released, it exerts a force on the ball, accelerating it forward. According to Newton's third law, the ball exerts an equal but opposite force on the catapult. But since the catapult is much heavier and more stable, it doesn't move significantly. The ball, unrestrained, is launched into the air with the energy transferred from the catapult's arm.
Then we have the air resistance strength. So air resistance is the force that opposes the motion of an object as it passes through the air. When taken in consideration in a projectile throw from a catapult, it does alter the trajectory of the object. The force affects the horizontal and vertical and decreases the displacement and maximum height that the object can reach. They oppose the acceleration in the x components and they work with gravity to bring the object down.
In a parabolic motion, when you don't consider air resistance, the x and y components of the movement can be evaluated independently. However, air resistance, which is also known as the drag force, affects both the vertical and the horizontal movement. So in the vertical component, the gravity and the drag force are the ones in charge of bringing the object down. But in the horizontal component, only the drag force has an effect on the trajectory.
These are some applications. You can see the velocity components, how you find them. Vx equals the initial velocity times cosine at that angle. Vy is initial velocity times sine at that angle. And you can also see the equations for the position in x, the position in y. And then you can see the equations including air resistance, which is basically just subtracting the opposing force. Euler's method is used to approximate velocity in the x and y components as well as position at various time intervals. The formula is given by the following formula, where yn represents the current value, h is the step size, which affects the accuracy of approximation, the smaller it is, and yn plus 1 is the new value we're calculating.
So the first thing we did to start the modeling of our trajectory was to put the videos on a tracker, which gave us these initial values depending on the time of velocity and displacement. And the initial speed of the first object, that was the yellow ball, when it was at rest, was of 0 meters per second. The angle we used for the throw of the catapult was of 43 degrees. And the output speed, which is the speed at which the ball went out of the catapult, was of 7.096 meters per second. The horizontal reach that we obtained, which means that the distance that the ball traveled in the horizontal, was 4.399 meters, which is 4.4 meters.
Here are the graphs for the tennis ball made by tracker. And also in the same as the yellow ball, we have an output speed which would be the speed in which the projectile leaves the catapult at an angle of 40 degrees. And with these conditions, the horizontal reach is 2.94 meters.
These are the values for the blue ball, which are given by tracker. And this is a summary of those values. When it is launched at an angle of 43 degrees, the output speed is 5.168 meters per second, and the total horizontal displacement is 3.10 meters approximately.
Here are the graphs without the resistance. We use MATLAB to generate them, and we can see a difference in the displacement because of the resistance.
In these graphs, we did consider air resistance, and in here we start to play to experiment with the value of K, which was the drag force. And in each of them, you can see that this displacement in X actually matches the results we got from tracker, as well as the maximum height, because the K that we used was the one that got more similar to the air resistance in our own parabolic motion, depending on the object.
And here you can see the different values of K, which we tested the balls at, and the different drag coefficients.
Okay, here's our MATLAB code we use to approximate the trajectories. First, we need to initialize the variables such as K, the angle, initial velocity, and the step. Then, with this information, the program calculates the initial velocities and positions. After this, using a while loop that stops when the Y position is less than 0, because we don't want the ball to go lower than 0, the while loop calculates the different values for the Y positions, X positions, and both the velocities. We use this by using Euler's method, and then we plot the given values for position in order to get the trajectories.
Our conclusions. What was the optimal angle according to theory and experiment to obtain a horizontal reach? In theory, the best angle to take a parabolic throw is to do it at 45 degrees, but we found out that a projectile could reach at least 3 meters with the 43 degrees angles that we use, which is the distance that we had as goal. While other variables affect parabolic shooting that are not considered in analytical calculations, the spin of the projectile can determine how much time the object stays in the air, the landing on the surface, and its influence on where the projectile lands, because it can bounce and end on somewhere else. And the higher altitude, humidity, temperature, and air pressure are things that have an impact on air resistance, which then have an impact on the X and Y components of the throw.
Okay, finally, in order to find the velocities in tracker, we need to do a few steps before. We need to import the video to tracker, then create a calibration stick, and end with a dimension we know in the real world. In this case, we use the tiles on the floor. This for the program to measure accurately the distances. Then we need to create a mass for the object, which will follow its trajectory. After this, tracker will calculate all the required data, including the initial velocity automatically. For the Euler's method, we use the same formulas as mentioned in the slide for the MATLAB code, which are the ones in this slide. Thank you.